Chapter 4, Problem 11. A mass of 1.5 kilograms of air at 120 kilopascals and 24 degrees C is contained in a gas-tight frictionless piston cylinder device. The air is now compressed to a final pressure of 600 kilopascals. During the process, heat is transferred from the air such that the temperature remains constant. We want to calculate the work input during this process. So the first thing here is we're going to treat the air as an ideal gas. And so therefore, we're going to use the ideal gas equations. So what we need is to be able to find what the R value is to use in the ideal gas equation. So we can find that out of table 1. So if you look back in the appendix, you'll find it's 0.287 kilojoules per kilogram Kelvin. So let's list what we're given in the problem. So here we know the mass is 1.5 kilograms. We know the initial pressure is 120 kilopascals. We know the temperature remains constant at 24 degrees C. And we know the final pressure is 600 kilopascals. So over here on the PV diagram, we can sort of look at what this looks like. We start at state 1, and then we compress down to a smaller volume, and the pressure goes up. So what relevant equations are we going to use? Well, obviously, we have to use the one for the boundary work, the integral of PdV. So the pressure here is changing, though, and it's not linear, it's not constant, it's changing. We have to find some kind of relationship between the pressure and the volume in order to be able to do this integral. Well, fortunately, that's where the ideal gas law comes in. So one form of there's many forms of the ideal gas law. I like this form here, where the pressure times volume over temperature remains constant. So you can set that equal at 2 different states. Now in this case, the temperature is constant, so we can sort of cross out the temperatures on both sides, and we can solve this for a ratio of pressures to volumes. The other form of the ideal gas law we often need is the following form here, especially since we're given the initial mass. So let's see if we can solve our integral. So here we know PV is MRT is some constant, so we can solve this for P and get this P is equal to C over V. C is a constant. That's our relationship we need to plug in here to solve our integral. So once we write that, we can substitute back what C is. It's either PV or it's MRT. In this case, we know the initial pressure and the volume, so we'll just use the PV. So here's one form of the equation we could use. But in order to use this, we would have to go back and we'd have to find the initial volumes, which is not a problem since we have the ideal gas law. However, since we know the pressures, what we're going to use is the equation right here that the relationship we start. So we can substitute V2 over V1 as P1 over P2 and rewrite this equation, substitute in our values, and then solve for the final work. Now this negative sign, what does that mean? In this case, it means that work is done on the system.